In this lesson, we're going to talk about reflections. And here's a beautiful picture of a reflection in nature where we can see the horizon splits the image into what's real and what is reflected on the water. And here's a couple others that are really neat photos that give you this idea of reflection, which most students understand. And we can't forget my summer home reflection on the lake. So a reflection is a transformation that mirrors each point of the figure. So it's a mirror image. So in this example here, we have triangle JKL, which is graphed here, and we want to go over the y-axis. The y-axis is the vertical axis. So this point here is 1 unit away from the y-axis, so it's going to end up the same distance on the other side. Point L is 1 unit away, so it would also end up 1 unit on the other side. Point K is 1, 2, 3 units away, so it would end up 3 units away on the other side. And this would be your reflection over the y-axis. Now, if you wanted to reflect over the x-axis, that's going to be the axis that is horizontal. So again, we count the distance from the point to the reflection axis. So we count 2 units, and it's going to end up 2 units above that axis. We count 5, it ends up 5, and we count 5, it ends up 5. All right, now here's an example where we have this given graphed segment, and they want you to reflect this over the y-axis. So what happens to this when you go over the y-axis? So in this case, -2, 3 is point P. If we go over the y, the only value that changes is actually the x value. So if you go over the y-axis, the x value will change signs. Okay, so that becomes a +2. The y value stays the same. So the rule when we go over the y-axis is we're going to change the sign of the x-coordinate. So the x-coordinate is -2, so it's going to become a +2 in our image point. This is a -3, it'll become a +3. This is a -3, it becomes a +3. So now when we want to reflect over the x-axis, I took these same coordinates and we're going to reflect them over the x-axis. So if this is the coordinate we're starting with, if we go over the x, we're going to switch the y coordinates. So over the x-axis, we switch the y coordinate. So this would be 2, -3, 2, -1, 3, -1, and 3, -5. Again, so what is the rule? If we go over the x-axis, the y value is going to change signs. And earlier this year, we talked about what a negative sign means in class. It means change the sign of, do the opposite of. So if the y value is 5, the opposite would be -5. If it was -3, the opposite would be 3. So we see this term of negative being the opposite and changing signs once again in this class. The y-axis will be changing the x value and keeping the y value the same. And if we did both at the same time, if you went over the x and over the y, you would change the signs of actually both coordinates. So far with reflections, we've reflected over the x-axis, the y-axis. There's 2 others that we're going to talk about, and that is the line y equals x. And the line y equals x would be a y-intercept of 0 and a slope of 1. So we go up 1 over 1 and continue graphing that line. Now, what we're going to do with these lines is we're going to count actually diagonal distances. So point B is a half diagonal distance from this line. So B prime is going to end up a half diagonal distance there. Also, what you'll notice is that these points are perpendicular to the line of reflection. So when we do reflections, they're perpendicular to it. I can't do this on the board, but if I were to turn my paper, you could actually figure out the perpendicularly, maybe a little bit easier to see. Point A is half diagonal distance away, so it's going to end up half diagonal back. Now point C is a little bit tricky to see on this particular image, so I'm going to try to draw these in here. And we see that it is 1, 2.5 units away. So 1, 2.5 units away. Sorry, half 1, 2 would be the reflection. And so we end up with this particular shaped graph. All right, now over here, let's see if it matches up with our image. So point B is 1, 2.5 diagonal distances. So half 1, 2 is going to be its coordinate. C is 1, 2, 3.5 diagonal, half 1, 2, 3. And then this would be a little bit tricky, but it would match up if you were to draw the lines in. So again, the important thing to know about this is you have to count diagonals when you have these y equals x and y equals negative x equations. By the way, why is this line going this way? The y-intercept is 0 and the slope is -1, which means we go down 1 and right 1. And that's why we get that particular line. Here's some examples of reflectional symmetry. If we were to draw a line vertical, Starbucks logo would be symmetrical. This one is actually no reflectional symmetry. It has rotational symmetry. And that'll be something we talk about later, but for some reason students get confused. This would be a no. This one has reflectional symmetry vertically. This has reflectional symmetry vertically here. If we don't include the word Gucci, just the symbol itself. Volkswagen would have vertical reflectional symmetry. The New Orleans Saints has vertical reflectional symmetry. Batman has vertical reflectional symmetry. And the Chicago Bears actually has horizontal. We finally see one with horizontal symmetry. Lululemon would be a vertical reflectional symmetry. So here are some other examples. So this would have a vertical. If this were an equilateral triangle, it would have 3 lines of reflection. This would have none. This would have 6. This would have none, and this would have 1 going diagonally through the face. This one here, if you connect the points, we have 3 lines of symmetry, and then if we were to connect the midpoints of those segments, we would have another 3 lines. I know it looks confusing, but I only drew 6 lines there. So if you have an equilateral triangle, a square, a perfect pentagon, a perfect hexagon, however many coordinates there are is the number of lines of symmetry. That's one of the shortcuts that we'll talk about a little bit more later.